Good morning, all. In this lecture, the topic is half wave and full wave control rectifier. In the previous lectures, we have already discussed about that what is your control rectifier and uncontrolled rectifier, and what are the different types of control rectifier, and what kind of power electronics element or device we use to making the uncontrolled rectifier, and what kind of power electronics elements we are using to making the control rectifier. So these this is the topic of half wave and full wave control rectifier. Now, uh, course objective is of this lecture is to introduce students to the basic theory of power semiconductor devices and passive components and their practical applications in power electronics. To familiarize students to the principle of operation, design and synthesis of different power conversion circuits and their applications, and to provide strong foundation for further study of power electronic circuits and systems. Now, these are the course outcome. After this lecture, I'm expecting from student that student will be able to understand the half wave control rectifier and full wave control rectifier and their working and analysis of their waveforms or their output waveforms. So I'm expecting from student that student will be able to understand each and everything. Okay, so we will discuss now how wave control rectifier and full wave control rectifier and what are the advantages and disadvantages. So different types of single phase control rectifier is half wave control rectifier, full wave control rectifier using a center tapped transformer, full wave bridge circuit, and a semi converter and full converter. So first, these are the single phase means you can divide converters into two parts. One is your single phase converter, and another one is your three phase converter. In single phase converter, you can see or check that the no half wave, in half wave, single phase half wave control rectifier or maybe a full wave control rectifier, you are using only one phase and one neutral wire. Okay? And the components we will use to making the half wave rectifier and full wave rectifier in single phase, the component required which is less than the component which is required in your three phase controlled rectifier, right? So these are the different types of your control rectifier. With control rectifier, full wave control rectifier, using a center tapped transformer, full wave bridge circuit, semi converter, and full converter. Now, different types of three phase control rectifier: half wave control rectifier, full wave control rectifier, semi converter, and full converter. Okay. So in semiconductor, we can call it half controlled bridge converter, or you can say full converter means fully controlled bridge converter. So, what are the basic principle of phase controlled rectifier operation? If you are using the term controlled with rectifier, it means you are not using diode. I have already previously discussed in our last lectures that if you are using controlling word in power electronics, that you are using something controlled device which can be controlled by its gate terminal or by its voltage or current. Okay, so if we talk about principle of phase control rectifier operation, that we are using SCR, GTO, or any other components. So basically, in generally we use SCR in phase controlled rectifier. So first we will discuss about single phase half wave thyristor converter registered load. So what is actually what is the uh, what is your single phase half wave thyristor control converter? So you can see that you can see that this is your half wave thyristor converter, in which you can see that we are using only one SCR. There is a transformer it has two windings. One is your primary winding and second is your secondary winding. In primary winding, the voltage is your VP, and in secondary winding, the voltage is your VS. So this is your primary and secondary winding, and you can see that in primary, the thyristor is connected to the secondary winding of the transformer, and there is a one load we are connecting through resistance. So this is all about your single phase half wave thyristor controlled converter. Now, this is your supply voltage and you are getting output voltage. So you can see that from the waveform, the input voltage is your AC voltage. So the positive half cycle is from 0 to 5 and the input voltage is your V1 and VM is your maximum voltage of your input voltage. So you can write it as Vs. Vs is your input voltage, Vm is your maximum voltage, and V1 is the voltage where at point at this V1 voltage you are giving the SCR, and we have already discussed about the SCR and what is SCR and how can it control your output voltage and what are the different terminals it has. It has three terminal. One is your anode, cathode, and gate. So through the gate terminal, you can easily control the output voltage of the SCR. So what do you understand by output voltage of the SCR? Output voltage of the SCR means that SCR is not giving any kind of output voltage until and unless you connect it with with supply. Okay, when you connect SCR with the input supply, then you will get the output voltage and you can control it by you controlling your gate terminal, right? So in supply voltage, you can see that V1 and V1 is your supply voltage and V1 is your input voltage. So at terminal alpha, you can control the output voltage. So what we are doing, you can see from the diagram that this is your input voltage, positive half cycle 0 to 5. If you are using one SCR, because SCR is also a unidirectional device, it can the current can be flow into the SCR from cathode to anode. The flowing of current in SCR is anode to cathode. Okay, so for positive half cycle, only one SCR will work, and you can see at this point alpha. Okay, alpha is your triggering angle or firing angle. Basically, this is called firing angle in SCR. So this may be it is less than 90 degree. You can easily see from the diagram that it is less than 90 degree. So it may be or 10, 20, 30, 40, 50, 60 or 70 or 80, 85, 82, any angle which you want, and it depends that how much voltage you require in the output. So at alpha you will trigger the SCR before triggering before this angle. If you are not giving any kind of firing or any kind of pulse on this on its gate terminal, the thyristor will not start to conduct. So the point is at this point alpha, the SCR will start to conduct. Okay, so you are getting output from alpha to pi. You are not getting this much of output. Okay, so by varying this firing angle, you can easily control the output voltage. Now the third waveform is your output current. So you can see from the diagram that the output current means that the current which is you are getting in the output. So it will depend upon that how long your SCR is conducting. Okay. So in this waveform we can see that when thyristor is triggered at point alpha, then it will conduct from alpha to pi. It will not conduct before alpha and it will not conduct at pi. Why it is happening? That it is why it is not conducting after pi, because the first thing is that the load is resistive, and in the resistive load the voltage waveform and the current waveform will be similar. And the second thing is that after pi, the negative cycle is appearing or negative voltage is appearing across the SCR. So if negative voltage is appearing across the SCR SCR, uh, come into the forward blocking mode. Okay. So when it comes into the forward blocking mode, there is no conduction, there is no current flow through the SCR. This is the ideal condition. Actually, for some time it conducts or it takes time to turn off. But in present scenario, there are many power electronic devices or power electronic components available which has very fast switching devices. So you can easily control your output voltage by fast switching of these devices. So this is all about your, wave rectifier and full wave rectifier. So this is your supply voltage, and if you talk about thyristor voltage, because 0 to alpha, thyristor was not conducting. If thyristor was not conducting, what does it mean? That the voltage will appear across the, there will be some voltage which will appear across the SCR. So this voltage is your VT1. This is called your thyristor voltage. Now, these are some equations by which you can easily uh, understand the working principle of phase control rectifier. So Vs is equal to Vm sine omega t. This is your input AC supply voltage. Vm is equal to maximum value of input AC supply voltage. Vs is equal to Vm upon root 2 RMS value of input AC voltage. V naught is equal to VL output voltage across the load. So when the thyristor is triggered at omega t is equal to alpha, V naught is equal to VL is equal to Vm sine omega t. So omega t is equal to alpha to pi. Okay. So I naught is equal to IL, IL is equal to V naught upon R, and omega t is equal to alpha to pi. So I naught is equal to IL, Vm sine omega t upon R, which is equal to Im sine omega t alpha to pi. So where Im is equal to Vm upon R, maximum value of load current. So this is all about your, how they control rectifier. Now we will discuss about the next topic, which is Morning, everyone. Um, Today's topic is control rectifier. So, in this lecture, we are going to discuss about what is your control rectifier, what is your rectifier, and where it is used, and what are the advantages and disadvantages of control. So, first, we want to discuss about diode and SCR. So, what is diode? Diode is a PN junction device. It has two terminal and two layers. Actually, it has one P layer and one N layer. And P layer means in this lecture we are going to discuss about control rectifier. So, what is first we have to discuss about diode. So, what is diode? Diode is a PN junction device. It means that diode has two layers and two terminals, but it is in uncontrolled device. Why this is uncontrolled? Because it don't have any kind of controlling terminal in its structure. So diode can be used as as a rectifier, but you can't use this diode to in control rectifier. So what is rectifier? Rectifier is basically used to convert from AC to DC. So this is rectifier, and what is controlled rectifier? Controlled rectifier means that we can control the output. So we will discuss it in detail in this lecture. Now, what are the course objective? The course objective of this lecture is that uh, to discuss about the different kind of rectifiers. It may be our controlled rectifier and uncontrolled rectifier and the course of outcome, and I'm expecting after this lecture that student will be able to understand the different type of uh, converters or rectifier, and what is the difference between controlled and uncontrolled rectifier, and what are the advantages, and which kind of electronic devices are used to control the to making a controlled rectifier. So these are the semiconductor devices, diode, control rectifier, advantages and disadvantages. So first we have to understand that what is rectifier. So rectifier, that the type of input you can see in this diagram, the type of input is a fixed voltage, fixed frequency AC supply. So what is happening? You are getting in the output, you can see that you are getting the DC output voltage, and this is your line commutative converter. Line commutative converter means if you are using AC in your input voltage, then you need not to apply any kind of another commutation circuit, because in natural commutation, because in AC the waveform goes into the negative direction, so that negative voltage can be used to commutate the SCR. So there are different type of line commutated converter. One is your AC to DC converter, AC to AC converter, AC to AC converter at a low output frequency. So first, if we go to the controlled rectifier or controlled converter, so first we have to understand that what is your AC to DC converter. So the diode, if you are using uncontrolled rectifier, or you can simply call it rectifier, then in this case you are using diode, because diode is used to convert AC to DC, but you can control the output of this rectifier because you are using diode. So what is happening that the diode rectifiers are referred to as uncontrolled rectifiers, and the diode rectifiers give a fixed DC output voltage. Each diode conducts for one half cycle, and the diode conduction angle is your 180 degree or 5 degrees. So, if you are using single diode, in that case, what you have to do, uh, in that case, only you can convert the positive half cycle of the AC voltage into the DC voltage. Okay. Now, if you are using two diodes in anti-parallel, then you can use, then you can convert positive as well as negative half cycle of the uh, negative half cycle of the AC input voltage into the DC voltage. So diode conduction angle is 180 degree and 5 degree. So diode, we call that diode is only conduct into the half cycle because you can see that diode conduct only for half cycle because it is a unidirectional. The current flow in the diode from p direction to n direction, and it can't be, it can, the current cannot be flow in the opposite direction. Okay, so that's why the diode is your one half cycle. Now we cannot control the DC auto voltage or the average DC load current in a diode rectifiers. So this is all about your rectifier, or you can say the uncontrolled rectifier. Now, what is your single phase? Now we will discuss about the half wave rectifier and full wave rectifier. So, what is your half wave rectifier? In single phase half wave diode rectifiers gives an average DC output voltage that is equal to Vm upon phi. Okay, we will discuss it later when we draw the waveform of half-wave rectifier, and we will analyze this rectifier, and you will see that the output voltage you are getting, which is equal to Vm upon pi. Single phase full wave diode rectifier gives now. Now, next is your application of phase control rectifier. So, before discussing this topic, it is very important to understand that what is the importance of that topic. How can we use these kind of rectifiers or diodes in physical applications? Okay, so these are some of applications which is used in which we use controlled rectifiers. So DC motor control in steel mills, papers, and textile mills employing DC motor drives, and AC fat friction system using DC friction motor, electrochemical and electrometallurgical processes, and magnet power suppliers, portable hand tool drives, and HVDC transmission. So these are, very vast field where you can use the phase controlled rectifier, and these are very important applications in this uh, technical world. Now, so, what is the classification of phase control rectifier? According to phases, because the uh, most important thing is that there is two phases. One is single and three phase, which is mostly used in electrical appliances. So it depends upon the appliance, which kind of supply it requires and how much voltage it is required. So what is your single phase control rectifier and three phase control rectifier? According to phase, we can divide these control rectifier into two parts. One is your single phase control rectifier and another one is your three-phase control rectifier. So, what is your single-phase control rectifier? In single-phase control rectifier, we use one single phase, and if you are using diode, then you have to replace the diode by the SCR. If you use only single-phase rectifier, then you can use only one diode or diodes. And if you are using three-phase control rectifier, then you are using three phases in the rectifier. Further, it can be classified into the more more different kind of control rectifier. Suppose half wave control rectifier, full wave control rectifier. So we can combine this half wave with single phase. So we your single phase half wave control rectifier and three phase half wave control rectifier, or a single phase full wave control rectifier and three phase full wave control rectifier. So like this, we can divide these you know uh, devices into these kind of classifications. So now we will discuss about the single phase controlled rectifier. So what is your single phase controlled rectifier? So good morning everyone. In this lecture we are going to discuss about control characteristic of single phase half wave phase controlled rectifier with resistive load. In the previous lectures we have already discussed about SCR, diode, already discussed about that. Now, now we will discuss about the waveform. We will do the waveform analysis of controlled rectifier, and which is your single phase half wave control rectifier. In single phase half wave control rectifier, we use one SCR and with resistive load. So the load is resistive, and we will use one resistance uh, in the load. So what are the course objective? Course objective of this the course objective of this lecture is to introduce students to the basic theory of power semiconductor devices and passive components, their practical applications in power electronics, to familiarize students to the principle of operation design and synthesis of different power conversion circuits and their applications, and to provide strong foundation for further study of power electronic circuits and systems. So after this lecture, I'm expecting from student that student will be able to analyze the output waveform of single phase half wave controlled converter. And these are the content of semiconductor. This lecture, semiconductor devices, rectifier, control rectifier, advantages and disadvantages. So we have already done this equation that the average DC output voltage is given by this expression, which is V output is equal to Vm upon 2 pi into 1 plus cos alpha. And we can obtain the control characteristic by plotting the expression for the DC output voltage as a function of trigger angle alpha. So, trigger angle alpha, if you take different angles of different values of firing angle alpha, you can see that the limit of firing angle is from 0 to 180 degree. So, 0, 30 degree, 60 degree, 90 degree, 150 degree, and 180 degree. So, the output DC voltage is VDM. And, if you calculate, if you put the value of alpha in above equation, you can see the output voltage equation is Vm upon 2 pi 1 plus cos alpha. If you put this values of alpha, you will get, if you put 0, then the output voltage will be equal to Vm. So the percentage of output voltage is 100%. Okay? Now, if you take angle 30%, 30 degree, then you will get the output DC voltage, which is equal to 0 which is the 93.3% of your input voltage. If you are taking alpha, which is equal to 60 degree, in that case, you will get 0.75 PDM, means the output voltage will be the 75% of your input voltage. If you are taking 90 degree, then the output voltage will be 50%. And if you are taking 120 degree, then the output voltage will be 25% of your input voltage. And if the angle is 150 degree, then the output voltage will be 6.69. And if you take the value of alpha is equal to 180 degree, then the output voltage will be 0. So at the angle of alpha is equal to 0, you are getting the maximum or 100% output voltage. But at the angle of 180 degree, you are getting 0 output. This is the control characteristic. So to draw the control characteristic, we will take angle alpha at on x-axis, and on y-axis we will draw the output voltage. So you can easily draw the characteristic that the maximum output voltage you will get at 0, and the minimum output voltage you will get at 180 degree, which is equal to alpha. So the control characteristic can be represented by this. Normalizing the DC output voltage with respect to VDM. So the normalized output voltage Vn, this is represented by Vn. The formula of normalized output voltage is Vn is equal to VDC upon VDN, which is equal to Vm upon 2 pi 1 plus cos alpha divided by Vm upon pi. So Vn is equal to VDC upon VDN, and which is equal to 1 by 2, 1 plus cos alpha, which is equal to DC output voltage. So if you derive an expression for the RMS output voltage, because we have done or we have already derived an expression for the average value of output voltage. So in this lecture, we will derive an expression for the RMS value of output voltage, that is your single phase half wave control rectifier with resistive load. So the RMS output voltage is given by V RMS is equal to 1 by 2 pi integration from 0 to 2 pi V naught square dot d omega t, and output voltage V naught is equal to Vm sin omega t, for omega t is equal to alpha to pi. So output RMS voltage is equal to 1 by 2 pi integration from alpha to pi Vm square sin square omega t dot d omega t and Q. So finally you will get the RMS voltage equation for the single phase half wave converter after integrating this equation. So this is the formula for the output RMS, and you have to put the value of output voltage, which is Vm sin omega t, because the load is resistive, and the angle firing angle is from alpha to pi. So you can put Vm square sin square omega t dot d omega t and root of this equation. After calculating this equation, you can easily get the output RMS voltage, which is by substituting sin square omega t is equal to 1 minus cos 2 omega t upon 2, we will get V output is equal to 1 over 2 pi integration alpha to pi Vm square 1 minus cos 2 omega t upon 2 dot d omega t. That is root of this. So V naught RMS is equal to Vm square upon 4 pi alpha to pi 1 minus cos 2 omega t d omega t 1 by 2. So after integrating, because the formula of sin square omega t is equal to 1 minus cos 2 omega t upon 2. So you will get putting the value of sin square omega t in this equation, you will get Vm square upon 4 pi integration alpha to pi 1 minus cos 2 omega t to root. So you will get Vm square upon 4 pi alpha to pi d omega t integration of d omega t, because one is constant, minus alpha to pi cos 2 omega t dot d omega t integration 1 by 2. Okay. Now, if you solve this equation, so you will see that what is the integration of omega t or constant. This is omega t as it is, limit from alpha to pi, and the integration of this cos 2 omega t, you will get sin 2 omega t, sin 2 omega t divided by 2, okay, and limit from alpha to pi root. So V output RMS is equal to Vm upon 2, 1 by pi, pi minus alpha, minus 2 pi minus sin 2 alpha upon 2, and you will get sin 2 pi is equal to 0. So output RMS is equal to Vm upon 2 integration 1 by pi, pi minus alpha plus sin 2 alpha upon 2. So V output RMS is equal to Vm upon 2 to pi, pi minus alpha plus sin 2 alpha upon 2. So this is the final equation of your output voltage of your single phase half wave control rectifier, where you can put different values of pi. So if you put the value alpha is equal to 0, so you can see that this term will be 0, and the output voltage will be Vm upon pi upon 2 root pi, and root pi will be cancelled, and you will get only Vm upon 2. So the output RMS voltage in the case of single phase half wave control converter will be Vm upon 2. We put alpha is equal to 0. Like this, if you take pi is equal to alpha is equal to pi, so this term will be 0, and this term also will be 0. So the output voltage will be 0. So in the case of alpha when alpha is equal to 180 degree, in that case also the RMS output voltage will be 0. So if you want to compare these equation with the equation of average output voltage, you can see in the chart, or you can make the chart, and you can analysis for the different values of alpha, and you can see the difference that how much voltage you are getting if you are changing the value of alpha. So it would help you to design if you design a circuit or design a rectifier. Okay, so this is all about your single phase half wave control converter. So now I think you are able to understand that what is your control rectifier, what is your uncontrolled rectifier, what are the control component, what are the uncontrolled components, and how can we analysis the half wave single phase half wave control rectifier, how you can get the waveform for the single phase full wave control rectifier. So these are the equations by which you can easily calculate or analysis the output voltage which you are getting from a rectifier. So in the next topic that we will discuss about our single phase full wave converter. In single phase full wave converter, if you are talking about uncontrolled rectifier, so in uncontrolled rectifier, we will use two diodes. One is for positive half cycle and another one is negative. If you are using controlled rectifier, then you have to use two SCR. One is for your control, one is for your positive half cycle. And so when we talk about the full wave converters, then the components are fixed. So this is all about your single phase half wave converter and single phase half controlled rectifier with the values of output voltage values of RMS and average. So in next topic we are going to discuss about what is the Power delivered to the load, that is your output DC power. And we have already derived the formula of output voltage and output power. So output DC power, average or DC output power delivered to the load. So P output DC is equal to P output DC into I output DC. So DC output power is equal to voltage DC and IDC, where output voltage is equal to average DC output voltage of output voltage, and I output DC is equal to IDC, that is average or DC value of output current. So power delivered to the load, we know the formula of power, P is equal to V. If you are connecting any kind of rectifier in the circuit, so the output power which is delivered to the load would be DC power into DC current. So the formula will be P DC into DC. And if you talk about the output RMS AC power, so output RMS AC power is equal to IRMS. This is your output DC power, which is delivered to the load, and load, and the power output is equal to V naught into IR naught RMS, and efficiency of rectification. So efficiency of rectification is dependent upon E beta, that is your efficiency. So efficiency, the formula of efficiency of rectifier is equal to P output upon P output AC, that is your percentage efficiency, and beta is equal to P output DC upon P output AC into 100. So the output voltage consists of two components, the DC component and the AC upon ripple component. So the DC component is your output DC voltage, and the AC output voltage upon ripple component P AC is equal to Vrms. Now the total RMS value of output voltage is given by, because the output voltage or current which we are getting from the rectifier, it has some AC component also. That's why we took the two different formulas. That one was your AC output voltage and another was your DC output voltage. So P output AC is equal to V naught RMS into I naught RMS, and AC output voltage is equal to your Vrms into Irms. So the total RMS value of output voltage can be given by squaring the two output voltage of a rectifier. One is your DC output voltage and another one is your AC output voltage. So Vrms is equal to root of V naught square DC plus V square RMS. So VAC is equal to VRMS is equal to root of V naught square RMS minus V naught square DC. So form factor, which is a measure of shape of the output voltage, is given by. This is very important formula. By this formula, you can easily understand that the performance of a rectifier. So this is the formula of form factor, which is a measure of the shape of the output voltage, which is given by alpha form factor is equal to V naught RMS upon V naught DC. So RMS output voltage upon DC load output voltage. So the ripple factor RF with respect to output voltage is given by RV. This is a ripple factor. The formula for ripple factor is given by RMS voltage upon DC output voltage. RMS voltage, if you talk about RMS voltage, you have to consider the AC voltage upon DC voltage. So form factor can be written as the value of V AC or V RMS voltage. You can get it from this equation, and you can put this equation in this formula. So you will get V naught square RMS minus V naught square DC upon V naught DC. So this is your you can simplify this equation, and you will get the ripple factor, which is equal to V naught RMS upon V DC. This is your AC component upon DC component minus 1. So if you take the ripple factor and form factor, you know that this formula is your form factor. So by replacing this equation by form factor, you can write the formula of ripple factor by RV is equal to root of Ff square minus 1. So current ripple factor Ri is equal to IRMS upon I naught DC, which is equal to IAC upon IBC, where IRMS is equal to IAC is equal to I naught RMS minus I naught square DC. So we are peak to peak AC ripple output voltage. That is, you can write this formula. VRTP is equal to peak to peak AC ripple output voltage. So VRTP is equal to V naught max minus V naught minimum. So IR is equal to peak to peak AC ripple load current. So this is your RMS value of the current, and this is your I naught maximum and I naught minimum. So this is your peak to peak AC ripple load current. Okay. So these are some formulas by which you can calculate or you can identify that what is the performance of your controlled converter. So now, yes. So this is your peak to peak AC ripple load current, and one is your form factor. We have done with form factor. Form factor formula, V naught RMS upon V naught DC. Next one is your ripple factor. So the formula for ripple factor, if anyone asks you to write the formula in terms of form factor of ripple factor, so you can write this formula. RV is equal to root FF square minus 1, and this is your peak to peak AC ripple load current. So peak to peak AC ripple load current is equal to IRTP is equal to I naught max minus. Now next formula which is very important, that is called your transformer utilization factor, which is very important, and in when you design any kind of circuit, that formula has very important role. So we have to understand what is your transformer utilization factor. So transformer utilization factor can be written as TUF. Okay? The formula of transfer utilization factor is equal to output output power, which is your DC power, divided by your input power, input supply. So where what is VS? VS is the RMS supply voltage and IS is the RMS supply current. Okay, this is your secondary current, because initially in our previous lectures we saw that we are using one transformer when you are doing rectification, and the rectifies a number of applications um, in electrical field also. So this is our waveform in which you can see that this is your primary current, okay, and this is your primary current and input current, PS, IS, VS, and minus IP. So it is going from minus IP to IP. This is your input voltage, fundamental current, and IS1. So what you can see that this is your supply voltage, PS, and this is your output voltage, and this is your input current which you are getting. So its peak value from minus IP to IP. So where Vs is equal to supply voltage at the transformer secondary side, Is is equal to input supply current, and Is one fundamental component of the input supply current. Ip is equal to peak value of the input supply current, and phi is equal to phase angle difference between the fundamental components of input supply current and the input supply voltage. So you can see that phi is equal to displacement angle, which is your phase angle. For an RL load, phi is equal to displacement angle is equal to load impedance angle, and phi is equal to tan inverse L omega upon R for an RL load, and displacement factor DF or fundamental power factor DF is equal to cos phi. So harmonic factor or total harmonic distortion factor, which is also very important. So IS1, this is the fundamental component. Fundamental components that you can see in the diagram, that fundamental component means fundamental component means that the basic basic current. Okay, so total harmonic distortion factor, it can be represented by THD. So harmonic factor Is square minus Is1 square upon I square S1, root of this, and you can see that Is upon Is1 square minus 1. So Is is equal to RMS value of input supply current, and Is1 is your RMS value of fundamental component of the input power supply. So this is your input power factor. So power factor is equal to Vs Is1 upon Vs Is cos phi, and which is equal to Is1 upon Is cos phi. So the creased factor Cf is equal to Is peak upon Is peak input supply current upon RMS input supply current for an ideal controlled rectifier. So these different components we have studied, and they have some ideal values. If the control rectifier had these ideal values, that it has very good performance. So if we talk about form factor for an ideal control rectifier must be 1. Meter, you will, if form factor is 1, then the efficiency of the control rectifier will be 100%. If you talk about AC voltage, then the RMS is AC voltage, and RMS must be 0 because you are rectifying your AC voltage. So you need pure DC in your output. So the AC component in the output voltage or current waveform must be 0, and the transfer a TUF, this is your transformation utilization factor. So this should be 1. The formula for this transformer utilization factor is output DC voltage upon supply. So it means if transfer utilization factor is 1, then the 100% conversion is you are converting 100% voltage which you are giving in at input side. Okay, so RF is your RV. This must be 0, and you can see the formula of RV. So RV is a ripple factor, and ripple factor must be 0, means that form factor is equal to 1. So in ideal case, the ripple factor is equal to 0. Okay? So ripple factor should be 0, and that is your total harmonic distortion, that must be also 0, because we don't require any kind of AC component in our output voltage. So total harmonic distortion is totally related to your AC component which you are getting in your output voltage, and power factor should be equal to DTF is equal to 1. So this is the your ideal components of your rectifier.